In this video, I will cover SystemVerilog for hardware design. That means the important SystemVerilog features and constructs which we need to understand to design our digital hardware using SystemVerilog. Hi everyone, my name is Gyan and I am a digital design engineer with 10 plus years of industry experience with multiple multinational companies. If you want to understand or learn Verilog, please do visit my YouTube channel VLSI Excellence. Now let's get started. So here we would be covering SystemVerilog overview, the new user-defined data types and standard, SystemVerilog new procedural statements, SystemVerilog two-dimensional port declaration, hierarchy and connectivity in SystemVerilog, SystemVerilog package, interface, etc. So now let's go through the quick overview of SystemVerilog. Before 2009, Verilog was the main language for RTL design and modeling, and SystemVerilog was the extension of Verilog and it was extensively used for verification purpose. After 2009, Verilog and SystemVerilog were merged into a single IEEE standard called 1800-2009 and which incorporates RTL designs and modeling as well as verification features. And following are the design features in SystemVerilog, whereas it includes the added new data types and relaxations of rules on existing data types, higher abstraction level modeling features, language enhancements for synthesis, interfaces to model communication between design blocks. And we are going to learn each and every important SystemVerilog features in details in the coming slides of this video. So now let's first understand the logic data type used in SystemVerilog. So I am sure that you are aware about wire and res data types in Verilog. So wire data type is a data type from Verilog 2001 standard and which is coming from net group. So Verilog 2001 divides the data types into two groups, net and variables. Wire data type is from net group, whereas register data type is from variable group. And here I would like to mention the important point is when we declare res data type, many of us gets confused that this is a flip-flop or a memory elements or a register. But that is not the case. The res data type doesn't mean it is a flip-flop or a register. The implementations or realization of hardware completely depends on our Verilog coding style. So having the wire and register data type in Verilog was causing a kind of ambiguity, and this has been solved in SystemVerilog using logic data type. Now let's have a look on this simple example. So in module experiment 1, if you see, we are realizing a AND gate, A in and B underscore in. And here we are using procedural assignment, procedural block to realize this AND gate. And when we use procedural block to realize the AND gate, our left hand side variables in the procedural block always has to be a res type. So here if you see output y underscore out is declared as res, whereas in second experiment 2, our realization of the same AND gate is using continuous assign statement, and in whenever we use assign statement, our left hand side variable has to be a y data type. So if you see y underscore out is declared as y. So the point here is both the RTL codes realize the same AND gate, but the output data type is different in both, and that is a misleading in Verilog. So to avoid this confusion, SystemVerilog standard came with the logic data type, and logic data type can be used in variable group or net group, which is inferred automatically from context. The realization of hardware gets inferred automatically from the context. Have a look at the same example. AND gate in the left hand side module experiment 1, the AND gate realization using the always block, and here the y out is declared as logic. In right hand side experiment 2, the realization of AND gate is using continuous assignment, and y underscore out is again declared as logic. So there is no ambiguity remained here. And we don't have to get confused with wire and res data type. The second important feature is enumerate data types for FSM. So if you remember in Verilog, if we have to declare the states for a FSM, we either have to use local param or parameter, and then we have to assign a particular binary value to each of the states. So sometimes what happens is we may declare the same value to two states, and that becomes a wrong functional implementation of the states. So if I want to say in single statement, it is cumbersome and many, and it may introduce subtle errors such as duplicated constant values. So the state declaration has been again improved, or it has been done in a different approach in SystemVerilog, which is better, and it creates less confusion and less functional errors. SystemVerilog introduces a new enumerate data type, which can explicitly list symbolic values of a set. Now, the previous FSM declarations can be rewritten as like this below, using a typedef enum. Define an enumerate data type for FSM states, and this is how we can define typedef enum. The name of states S0, S1, S2, and the state type. This is just what the name for the states. Actually, it is now the state underscore type has become a new data type for the states. It is a data type which has values S0, S1, and S2. The important point again here is the S0 by default takes the value 0. So S0 here is equal to 0, S1 is 1, and S2 is 2. If we do not define any values to these states, they will take the default. The first state will take the default value 0, second 1, and third 2. But if we have to declare, or if we have to define a particular value to the state S0, we can use the similar approach. S0 is equal to x, and then S1 is equal to x plus 1, and S2 would be equal to x plus 2. That is how it will go. So here if you see, we do not have to use the local parameter or parameter constraints, and the state, the value, the numerical value for the states will also automatically get enumerated. Default from 0. If you give a particular value to S0, then the values start from that particular values by incrementing 1 to each and every state. Now, our present state and next state variable would be type of state type, which would indicate the state name S0, S1, S2, and so on. So this is much clear and more descriptive, and this is the second enumerate, and this is the enumerate data type for FSM. This is the second important feature which was incorporated in SystemVerilog. Now, here the another important feature was related to the procedural blocks. If you see, Verilog has only one procedural block called always keyword, that always start with always keyword, right? So if we have to implement a register, our coding style would be something like this: always at positive edge clock or negative edge reset, we implement the reset value, and then we assign the actual input value. So this is the code for a flip-flop. If we have to implement a latch, again we can start with always, but here now the sensitivity list, how we declare the variables in the sensitivity list gets changed, right? And then we have to use a incomplete if else statement. If select op2 is equal to a, otherwise it will get the previous value. There is no else part of this. So this kind of coding style will infer a latch. If you have to implement a combinational mux, the coding style would be something like this. The sensitivity list will include select A and B, all the variables from the conditions as well as the right hand side variables, and then there would be a complete if else statement. So these, using the same always keyword and making use of three different coding styles, we could infer a register, a latch and a mux. But sometimes what happens is, by mistakes we want to implement a mux, but we results in getting implemented a latch. And in this case, since the keyword is same always, the compiler doesn't throw any kind of error that you intended to realize a mux, but you are getting realized, but it is getting realized with the latch. There won't be any compilation error because there is the same always keyword. So Verilog always block can synthesize to combinational latch or a sequential register logic. It is controlled by the sensitivity list and Verilog coding style. Such ambiguity can cause problems in the design and can lead to incorrect logic implementation. SystemVerilog adds specialized or procedural blocks to model combinational latch and sequential logic. So now let's see how SystemVerilog improves this ambiguity. So in SystemVerilog, there are three always procedural blocks differentiated with different keywords. Always underscore com to realize or to implement the combinational logic. Always underscore ff to realize the flip-flops or the registers or the sequential elements, and always underscore latch to implement a latch. So what happens if we use always underscore latch, but our code inside doesn't obey or doesn't implements a latch, then the compiler throws an error. It says that you wanted to implement a latch, but your code inside the always underscore latch block doesn't implement a latch. Or for example, always underscore ff, you want to implement a ff, but your code inside the always underscore ff block doesn't obey the coding style of implementing a flip-flop, rather it obeys a combinational logic or a latch. So in that case, the compiler will throw an error. So it will become more efficient or more easy to catch these kind of errors using these three different always blocks in SystemVerilog. Now let's have an example. So here we want to implement a registers, so we would use a always underscore ff block. Again, the sensitivity list will contain the positive edge clock or negative edge reset, and it is similar to the Verilog coding style. Then we want to implement a latch, we would use always underscore latch always block, always the keyword, and then mux. In mux we would use always underscore com. And then here comes our top level modules where we are going to use this. This is a plus b, and then we have addition, the addition, then we have our latch, and this third block is a flip-flop. So here the important issue in Verilog, which was unintentional latch inference because of wrong coding styles, gets eliminated completely. You might have heard about unintentional latch inference. That is one of the example I could give you at this time so that you could relate it. And that kind of problems is solved in SystemVerilog using always underscore latch construct. Now let's move to the next important improvement in SystemVerilog, which is two-dimensional port declaration. In Verilog we cannot declare two-dimensional port. For example, here we want to declare a x underscore 2d 31 down to 0, then 63 down to 0, but this is not permitted in Verilog 2001. So to have this kind of features in Verilog, we had to use a different approach, which is we have to somehow make it unidirectional, x underscore 1d. So here the number of bits 64. So you can see here that there are 32 locations. There are 32-bit variable with 64 locations. right? This kind of a FIFO which has 64 entries and each entry is 32 bit. Now those many bits we have to declare as a part of one dimensional array, and then we have to reconstruct it, or we have to make it again into two dimensional by using additional logic, something like this. We have to reconstruct 2D signal inside the module. So again we have to 64 locations, so we have to construct a two dimensional array, something like this. So this was again an extra or overhead while using two dimensional arrays, two dimensional ports in Verilog. Two dimensional arrays are possible in Verilog, but two dimensional port declaration is not permitted. And this has been improved in SystemVerilog, and in SystemVerilog we can directly declare a two dimensional array like this. Now let's come to the another important improvements in SystemVerilog, which is port connectivity. So when we instantiate a module, a child module inside a parent module, we have to do the port connections, and Verilog has its own styles of port connections which has some flows, and those flows have been eliminated or the effect has been removed in SystemVerilog using a different approach. So Verilog offers two port connection options: ordered port connections, but it has a risk of incorrectly ordered connections; named port connections, which are safer but very verbose. So let's take one example. Here we have an example demo underscore counter which has some ports: input, logic, clock and reset, and load, input, data and output, count. So when we instantiate this child module inside a parent modules, either we have to use the ordered connection approach, or we have to use the named connection approach. So first approach here, this is ordered. Here the first port in this demo underscore counter is clock. So we have to connect the clock to the first. The second one is reset. The third one is load. The fourth one is data, and the fifth one is count. If we change the order, then the functionality will completely be different, and there would be lot of compilation errors, right? So if we order in this first way, this is fine, but sometimes what happens is by mistake our orders gets incorrect. So for example, here instead of reset, our second port is load and the third is reset, which is a wrong order. So these kind of issues are common in Verilog when we use the ordered connection approach. The second approach in Verilog is named port connection. So we have to dot clock, we have to have dot, then the child port name, and then the signal which we are connecting at the parent instantiation. So this is again a safe approach, but it is a verbose. So SystemVerilog improves this approach by using another method, and which is dot name. The first approach is dot name, where signals and port name matches just use name once. So the child module here, let's say, has name clock, and where it is getting instantiated in parent module, also we have the signal name same. So in that case, we don't have to use dot clock, then in bracket again we have to assign clock. We don't have to use this approach. We can use dot and directly name. But whenever there is a change in the child port name and the parent signal name, then we have to use dot clock and in bracket clock. This is similar to the Verilog approach. So the SystemVerilog makes it a little simple by using just the dot name if the port name and signal name are same. The second approach, and another important point, is SystemVerilog also permits to use both approaches in mixed manner. So if the port name and the signal name is same, then we just use dot data underscore in. If they are different, then we use in bracket we connect the signal dot ld bracket load. So the mix approach is also possible in SystemVerilog. The second approach of port connection is dot star. If the signals, if the port names in our child module and the signals in our parent modules matches, they have the same name, then we just use dot star. This will connect each port with the signal without explicitly naming them and mentioning in the instantiation of the child module. So it simplifies. For example, let's say if a module has hundreds of signals, so we don't have to connect, or we don't have to write the 100 lines or the 100, we don't have to do the 100 port connections. We can directly use dot start if our signal name and the port names of the child module are same. And if there are few ports which have different name than the parent module signal names, then we can also use a mixed approach here. We can use dot star along with the ports which have different name. We can connect them using the named approach. So this is again the connectivity or the instantiation of the modules gets simple in SystemVerilog by making use of this dot star and dot name approach. Now let's understand the another important feature of SystemVerilog, which is package. What is package? So first let's understand, or let's have a reference to the Verilog. In Verilog we use tick include compiler directive to share declarations among modules which can cause issues. Right, SystemVerilog has a new option for sharing declaration which is called package. What is a package? A package is a new design element similar to a module. It is a design element. We can implement it like a separate module, and it must be compiled separately or must be compiled before elements which reference the package. So if this package is used in different modules, this package must be compiled first so that the other modules can get reference to it easily. They contains declaration to be shared between elements, types, variables, subroutines. We can import package declaration in different approach: explicit, specifically named approach, and implicit, all using word-called entries, and directly access a declaration using the scope resolution operator, which does not require import. We will see how these things can be done using some examples. So here is a SystemVerilog package. We have a package called mytypes, and it defines a enumerated data type called mode_t, which has two values, start and done. Okay, and here our package ends. Just for the explanations, we just have this first one enumerated data type mentioned or declared in this package. Now how we can import this message? The explicit import method. So here we have our module demo1, and in this demo1 we want to use this package, or we want to import this package. So the keywords would be import, then mytypes, scope resolution operator, then mode_t. This is the variable we want to import from this package. Okay, mode_t, and then we will assign a variable name mode, which is type of mode_t, which has the values start and done. This is explicit import of the package. Then we have wildcard import. So here in the first one, explicitly we are importing the mode_t data type only. In wildcard import, we are importing everything. Import mytypes, scope resolution operator, then star. So here everything from this package gets imported in this demo1 module, and from there we want to declare a variable mode of type mode_, and this is called wildcard import, and this gets resolved as package, then mode T, and then mode. This is how when we compile it gets resolved. Now comes to the important features of SystemVerilog, which is interface, and this is my favorite one. The benefits of using interface is, by making use of interface, we can reduce the port list of the modules. It improves readability and it enforces a structured communication between the modules. So it becomes very easy when we integrate multiple modules. First, we are going to see an example where we do not use interface. So we have a module CPU core, which has some global inputs, clock, reset, and then some inputs like ready and read data, and then outputs write data, request, mode, and address. So you can understand it something like there is a CPU which is trying to read data from some memory. So it has to send a address, it has to send a mode, whether it is a read or write transactions, and if it is a write transaction, it has to send a write data, and if it is a read transfer, it will receive a read data and also a ready signal from the downstream memory, right? Whenever the memory is ready, then the CPU can go and access the data. So these are the signals, the obvious signals at the CPU core port list. And then here we have the memory. Again, it has some global signals, clock and reset. Then it has a request, a new request, whether to read or write the memory. Then mode, read write, address, input address, and input write data. And it will send, when there is a read transaction, it will send the output data, and it is also send a ready signals whenever the memory is ready for a new transaction. So when we integrate these two modules, we have to again declare these variables, and we have to instantiate this memory and CPU, and then we have to connect these signals with the port names. Here again we are using the named port connection approach of SystemVerilog, right? So we have to declare. So if you observe an important point here, our signal list or port list is same in CPU core module, memory module, or top module, right? This is common port list and signal list. And now let's assume we have to add a additional signal here in CPU core. Let's say a type signal, type of transactions, whether it is a single transaction or a burst transaction kind of signal we have to add. Then that signal will get added here in CPU core. Then we have to go and change in this module memory and our top module, right? Again, also in our top module. So we have to make changes at three places: CPU core, memory module, and top. Three places we have to make a change whenever we have to add or let's say remove a signal. Using interface, this gets simplified. What we have to do is we have to declare a interface, and in this interface we are going to declare, we have to define an interface, and we will define all these signals used in this interface which are common across different modules. So the ready, request, read data, write data, mode, address, all those things now are part of this interface. And now how we can use this interface in our modules? So this interface can directly be used in the port list of a module by using the interface name and an instance for this. In memory again, interface name and instance, and similarly in our top module. And now when we instantiate our memory and CPU port, we don't have to use the complete list of signals, we just have to use this interface. In top module we again instantiate this interface IFA bus underscore A, which is type of IFA interface, and this bus underscore A we will put in the port list of memory and CPU core. And in this way, the memory, CPU core and top module will get connected through all these common signals which we have defined in our separate module. And in that module we have defined our this interface. So now whenever we have to add a new signal, we just have to add our signal here in this interface list and it will get connected across all the modules. So this is a better approach, a best practice to code our design with minimal updates. Now a interface we can declare not only with just the signal names, but we can also have parameters declared with our interface name. So here if you see our interface underscore AB, we have a parameter passed to this interface which is width, and then we have our input bit clock and the signals declared here. So this is a parameterized interface declaration. How we can use this? Now to use this interface in top module with different parameter widths, we have to declare two instances of it. The first instance, narrow interface, which is having the parameter width 15, and the second instance of this interface, which is wide interface, is having the width as 63. So again, we can have this interface as a parameterized interface, which again helps us to code our design in a better, efficient way. Now, how we can use this interface? This is again little bit further detail. To use this interface, for example, we have, so in the memory, again in the port list, we have our interface. Now, let's say we have to decode in the, so the interface have a mode. I am assuming it is a read and write. So in the memory, how we can decode this interface or we can access this interface? We have to access this interface by interface name, then the signal name. So if this value is 0, then we are having another variable declared as a read. So our read would be high. If the mode is 1, then our write would be high. And if it is a write operation, then our memory will get new data. So in memory, the address, how we have to decode the address, the interface name dot address will get bus dot write new data, right? And when it is a read operation, our read data bus dot read data, if it is a read, it will get memory bus dot address, otherwise it will be 0. So this is how, by making use of this interface, we can code our module memory. But there is an important issue here. If you see in interface, we have declared all signals with data type logic, and we haven't defined the direction of any of these signals. For example, in memory, for memory, the signal address is an input, but for CPU core, address is output, right? So if we don't define names, then by making use of the coding styles in these modules, this interface signal flow gets connected or the data flow happens in a proper way. But suppose in our coding styles or while coding the memory, instead of directly using this address, if we start driving this address and then CPU is also driving this address, then there is a functional issue. So this interface with only having these signals without directions can cause some functional issues in big designs. So to make sure that we don't have these kind of issues, we further enhance our interface by making a concept of mode port. We will see the concept of mode port in our next slides. So this is one flow I have mentioned here. Let's say CPU can accidentally drive ready, and memory controller can accidentally drive address without direction enforcement. Then there is a functional issue and it becomes a big problem in large designs. And this has been improved by making use of mode port. Okay. So mode port is again an enhancement in interface, and mode ports create different views of an interface. It specifies a subset of interface signals accessible to a module, specify direction information for those signals. Let's have an example. Here we have a interface mode interface A. It has 4 signals A, B, C, D. Now these signals can have different directions depending on different modules. Let's say we have a master, and in that master module our signal A and B are inputs and C and D are outputs. So we have to define a mode port, a module port, and we are giving a name. This is a master module or a master view of this interface where input A and B are input and C and D are output. Similarly, we have a slave mode port where C and D are input and C and D are input and A and B are output. And again we have a subset mode port where input is B and output is A. So here we are defining different views of this interface with directions. Okay, so it will have benefits in enforce signal directions, improve readability, prevents accidental misuse of the signals, or it makes our verification easier. So now how we can use these mode ports? Again, here is an example, the same example, and we have our module top. In this top module we are instantiating our master module or master child module. Okay, this top module is our parent module and master is our child module. So what we do, mode interface A, we define our interface, we instantiate our interface here, and from this interface we choose the master mode port. So from this interface instance we connect the ports of our childs to the mode port master, right? So this is how we can use this mode port in the instantiation of a child module. So now this master port is coming with the direction of the signals. The second is we can use in the module definition itself. In the first one, it was the mode port is used in module instantiation, and we can also use it in the module definition. For example, we have the same our interface, but here in this module slave definition itself, we are connecting the slave mode port to the port list of this slave. So again, it is coming with all the signals including their directions. So this is how using the mode port in interface makes our module definition as well as module instantiations and then overall our complete integrations more readable, more accurate, more easy, and there would be less rooms of any connectivity errors. So if you see the advantage of SystemVerilog interface in Verilog, as I described, for any addition of a new signal, it has to be manually changed everywhere that wherever that module has been instantiated, and SystemVerilog made it easier to add new signals in the interface log for existing connections. Similarly, they encapsulate connectivity. An interface can be passed as a single item through a port, thus replacing a group of names by a single one. We just have to use a single interface name instead of using all the signals in the port list, right? They can contain parameters. As I mentioned, they can have parameters, they can have constants, variables, and also they can be parameterized. Interface can be parameterized. It also includes flexibility. An interface may be parameterized, right, in the same way as a module. It provides directional informations by making use of mode ports and timing information, clocking blocks. I have not covered the clocking blocks here, by the way. We will cover it in some next videos. And interface can contain parameters, variables, functional coverage, assertion, task, and functions. You can have everything in the interface. So it is also very useful for verification purpose. Interface can also contain procedural, initial and always blocks and continuous assignment statements. So this was the overview of the new features added in SystemVerilog, which are very user friendly for hardware designers. I hope this video was helpful for you. If you liked it, please do not forget to subscribe my channel and share the video with your friends. Thank you very much.